Algorithms are like diamonds. Well, algorithms represent that aspect of software in which we have crystallized techniques that have a strong mathematical basis and about which we know a great deal and can say a great deal.
The EDSEC had begun to work in May 1949. It was possible to exhibit the contents of the memory on a cathode ray tube, like this.
The Industrial Revolution effectively freed man from being a beast of burden. The computer revolution will similarly free him from dull, repetitive routine.
And when I go back to 1960 again, you have to realize those are very slow computers and very slow disks, so you had to use those resources with great care. So the number of things became no-nos. No, don't do it. It says, know how to do it, to make it work right.
How smart can machines become? What are the limits of artificial intelligence?
Well, I see no limit short of human intelligence, and then with faster machines one could do in a short time the equivalent that a human could do in a very long time.
I've learned not to be too optimistic and to realize that, doing something worthwhile is tough.
We were trying to make computing as simple as possible. In the late 1960s, Dennis Ritchie and I realized that the then current operating systems were much too complex. We attempted to reverse this trend by building a small, simple operating system on a mini computer.
Well, what we wanted to preserve was not just a good programming environment in which to do programming, but a system around which a community could form, fellowship.
If you want to know about the future, you need to ask the young people who will create it. Young people don't know what can't be done, and so they go ahead and do it.
I think in many domains of computing, actually, one has to be very suspicious of the elegant solution.
Herb Simon comes in and says, over Christmas, Alan Newell and I invented a thinking machine. What could he possibly mean by that? First of all, what does he mean by a machine? And then what could he mean by that machine doing thinking?
You can buy a pretty substantial computer for $1,000. And it'll last you for about 3 years. And that's about 1,000 days. So a day costs $1. This is 1 day's worth of computing.
In the Stretch project, we had a chance to build a machine for speed without worrying about cost. And this drove us to attempt things nobody had ever attempted before.
What now we have to do is find a way to identify things with identifiers that have persistence. We need to find a way to distinguish between that which can be safely ephemeral and that which should be long-lived.
One of the things that I've observed over the years is that doing a project, building a machine or a compiler or any of these things, shows up many wonderful new solutions, which are usually kind of half-baked. They don't quite work, but you have to get it out and meet the schedule. When one has a little time, then one can start to go look at it and try and build a theory behind it.
Today, we can put every single digital bit of every piece of information that you receive, all the videos, all the television, all the things that you read, over the course of your lifetime, on a few disks.
And that's just the start of those videos. There are going to be a couple more of those in the next few days. I want to invite the next panel up. This is a panel on systems architecture, chaired by Dahlia Malkhi. Come on up, Dahlia, and grab a seat and bring your panelists up. Dahlia is a principal researcher at Microsoft Research. And look at the rest of her group up here, because we have one more little video clip. So anybody in the room has ever been an interview and you thought, oh boy, I hope that doesn't come looping around to me in a couple of decades? Just show of hands here. Yes, a few of those. Well, 50 years tends to pass in a long time, a decade or two, and the like. So we have just a little video clip that will run right now. So let's run that clip. See if you recognize this individual.
basically only understands numbers. I mean, you put numbers into it, and these represent something.
I see. So once you're able to talk to the computer, then what next?
Well, the next major problem is that of the ability to interact with the computer.
And these computers cost a lot of money.
Yes, indeed they do. They're between $300 and $600 an hour. So
you don't want to waste time.
No, we don't want to waste time. So we, as most other centers, have resorted to a procedure of batch processing.
Oh, I see. So you solve everybody's problem in turn.
Well, in a batch. A group of people like catching a bus. And the computer calculates this batch through and produces an output tape, and then the output tape is brought over to the computer, and the results are printed out.
I just want to say it was an act of extreme patience and grace by one of our panelists. And as I was watching that for the first time, I kept thinking of the thought bubbles above Fernando's head as he was listening to this absolutely incomprehending journalist. So with that in mind, I will now get off stage. Dahlia, the podium is yours.
Thank you. And good afternoon, everyone. Thank you for joining us. Thank you for...
Mike. Now you're on.
All right. Once again, good afternoon, everyone. Thank you for joining us. Thank you for coming back from lunch. My name is Dahlia Malkhi. I'm from Microsoft Research here in the Silicon Valley. And the Turing panelists here with me on stage are Fernando Corbato, also known as Corby, Professor Emeritus of Electrical Engineering from MIT. Next is Ken Thompson. He's a distinguished engineer at Google and a former member of the technical staff at Bell Labs. Next is Alan Emerson, a professor of computer science at TUT Austin. And last is Joseph Sifakis, who has multiple roles. Currently a professor at EPFL in Switzerland. He's also a CNRS research director at Grenoble, France, and the founder of Verimag Laboratory. It's an incredible honor to chair this panel. It's also a quite intimidating role. Our panel is called Systems, Architecture, Design and Verification, the Practice in Research and Research in Practice. Kind of hard to think what is left out of it. As I was going through the award announcements for each one of you on your past awards, one word that came into mind immediately and stood out is impact. You all contributed to the success of the computing world in extraordinary ways, not just through groundbreaking results in science, of course, but also through direct impact on real-life systems. Furthermore, you've all personally been involved in the effort to carry this influence into the practical world. So I thought it would be interesting to spend this panel and share your thoughts and experiences and lessons on the boundary between research and practice and how they interact with each other and feed one another. I will ask you questions like, in hindsight, would Turing universal machine had the same impact if it had, let's say, 20,000 instructions instead of the very few elegant that it did? Or is the realization of Moore's law, which, after all, has been predictable for years and years, and yet, in realizing it, there's tremendous ingenuity and effort involved. Is that pure engineering, or is there science in it? And things like that later on. But I thought we would start by going around the panel one by one. We'll do it in chronological order of the awards, and spend a few minutes each reviewing your works in retrospect in this slide. So we'll start with Ken Thompson. In 1983, you received with Dennis Ritchie the Turing Awards for the development of generic operating systems theory, and specifically for the implementation of the Unix operating system. Would you please share with us?
Thank you very much. Well, to quote Galaxy Quest, I'm just jazzed to be here. I wonder what would happen if you could grab Turing in 1954, just before he died, of course, and drag him up here, skipping everything between, and then try to teach him what's gone on in his absence. You'd have to tell him about operating systems because he's never heard the word. You'd have to tell him about compilers. He's never heard the word. And the other thing he was big in was games. He actually wrote the first computer algorithm for playing chess and played the first computer chess game. I don't know if you guys know that. The computer was simulated by him, by hand. It wasn't a real computer, but it was a real algorithm. So I guess you don't have to tell him about games. But if you want to tell him about operating systems, what you do is you open a box from Dell, I guess, or someplace like that, hand him a computer and a stack of install disks, and tell him, it's your turn, go ahead. And it would be probably a week of Turing time. You understand that's different than normal time. And he half of that time he'd be on the phone with waiting for a computer answer kind of thing. So then he'd get his computer up, maybe, but probably with help. He'd put it there and he'd sit and think for a while. And before he got his first 3 emails about a prince in Nairobi or someplace like that, or an advertisement for Viagra. After which his computer would be part of a botnet sending this thing out because, of course, he didn't have a firewall on it because no one told him. I'm basically trying to, all of the talks up to now have been rosy future, beautiful talks, and I'd like to counteract that slightly by just saying that, it's not all rosy, that I feel now kind of probably the way one of the pioneers of television would feel if he came and saw Maury Povich or something like that. Languages and operating systems. So the next thing you teach is Turing would be languages, and it would be a concept. You could grasp the concept, but then you'd hand him a C++ manual. And I think we, talk about just a couple of weeks of Turing time. I think that would be a lifetime gone, is over. Then you teach them networks. These are probably the 3 biggest advances in computers: languages, operating systems, and networks. But networks are still are good. Unfortunately, they open you up to a horrible world out there. And there's some really, really bright spots like Wikipedia and things like that. But so I'm still optimistic about networks.
I'd hate to ask you what you think about Perl, if that's what you think about C++.
No, later.
Later, okay. Okay, Fernando Corbato, Corby, in 1990 you received the Turing Award, not unrelated, for your pioneering work organizing the concepts and leading the development of the general purpose, large-scale, time-sharing and resource-sharing computer system, CTSS and Multics.
Yeah, thank you. I'm going to use the podium because I want to look at my notes. It doesn't help to drop them either. Well, I was asked to reflect a little bit about the award and the early things. First of all, I think this panel is a pretty eclectic one. We're kind of the also-rans. It's a crazy combination, but with both theory and practice in here. But the thing that I reflected about was I got my award in 1990. The work that I actually did was began and was during the decade of the 1960s. And the thing that I had to remind myself was gee, that didn't look like it was that important anymore, except that it is, because it looks so ordinary, because it's what we did in those days has become omnipresent in everything we do today. The thing that I think is most profound is that we were in an era where computation was very, very difficult to do because of the act of programming was so hard. In the very early days, in the 1950s, which I also had a chance to experience a little bit, computers were more accessible. You could get your hands on them. You would be able to work with them for maybe all of 20 minutes at a time, flipping switches, putting in punch paper tape or something like that. By the 1960s, computers had become very inaccessible and very difficult to use because everyone was so worried about the economics that they had made them batch processing machines, and you could maybe get one run a day or maybe 2 runs a day to discover you'd left out a comma somewhere. It drove people crazy trying to write complicated programs. Fortunately, and we also had to deal with such interactive things as punch cards, punch paper tapes. There were no computer screens, and people probably have gratefully forgotten computers were very flaky. Many of the early computers would run for all of 20 minutes before they crashed. Later that got to be a day or 2 sometimes, but they did crash. And there was no data storage, no online data storage. Everything was lugging around either a deck of cards or a magnetic tape. It was a pretty far cry from the world we live in today. Fortunately, John McCarthy, the late John McCarthy, who died late last year, had the insight to articulate and largely conceive of a different world, namely one of time sharing. And John got his Turing Award for all of it, largely for his AI activities, but among others, he was the inspiration for articulating the vision of time sharing. He gave a lecture at MIT around 1961 in which he spelled this out quite well, and inspired a lot of us, including myself, to get involved. My first involvement was through CTSS, which was largely a hack to sort of put together an early mechanism for time sharing on a batch processing system running on an IBM 709. It was sufficiently successful that we were inspired to keep building and wheedling more memory, more space, and it gradually evolved into a sequence of events. It led to people like Licklider had gone down to Washington with a vision of starting time sharing. He went to ARPA, had lots of money at his disposal, and shrewdly invested in about a dozen places around the U.S. I've lost count exactly, and seeded time sharing. But MIT was one of the places where he caught us just at the right time. And Bob Fano at MIT came to the realization that starting a project was the way to begin to have an impact, and that's where Project Mac got started. And Bob Fano, who I still see about once a week, had extraordinary vision and encouraged us all to participate. it gave us also the place where we could start a new operating system, which was meant to supplant and succeed CTSS, which were then using as a kind of a workhorse demonstration. And that new operating system was called Multics. We intrigued Bell Labs into getting involved. Ken Thompson was among them, and among the people that worked on Multics. And it was a great vision. We almost bit off. We had a hard time getting it rolling, but we eventually did. It succeeded and ran. There were maybe 200 instances of the machine system, about 72 or 75 sites around the world, and it lasted for over 20 years. We had a lot of impact through the ideas that we were able to articulate, and we, I think, set the standard. It looks, in retrospect, we've influenced the world of interaction. We see it today in our personal computers and in our general approach to computing. And I think the legacy of those early systems is still with us, but fortunately, in many ways, we've moved on and things have gotten better and better. I think I better stop and let the panel go on. Yeah.
Thank you. The next two shared also with Clark the 2007 Turing Award. And these are, of course, Alan Emerson and Joseph Sifakis, for your role in developing model checking into a highly effective verification technology that is widely adopted in the hardware and software industries. So let's do this by alphabetical order. Professor Emerson, you go first.
Okay. First slide.
Here.
Now, how does this work? Green? Okay. I am a formal Methodist. That is to say, I work on formal verification of computer programs and computer systems. The broad situation is this. Are we missing a slide? Yeah, we are. The broad problem is that computer programs, computer systems are everywhere, but they're buggy. Not only are there a lot of programs, each program typically contains bugs. Naturally, we would want to try to test the systems in order to identify and eliminate bugs, but that doesn't work. You usually can't identify all the bugs, and it would take too long. In 1960, October 1960, there was nearly a nuclear war. This was in Risk Digest. The U.S. ballistic missile defense system interpreted the moon as a massive incoming attack. Fortunately, there was a human in the loop, and there wasn't automatically launched a counter strike. some programs, it's not that serious if there are errors. In other cases, it can be life-threatening, safety-critical, economically very expensive. And in case of the moon, as big a catastrophe as you can imagine. So the suggested remedy is formal verification, where we view programs as mathematical objects, and we specify correctness in some formal language or logic, and then we use that logic to establish or prove that the program meets its specification. Now, Turing actually got his finger very early on into the issue of verification. He wrote a paper in 1949, it was more of a tech report, called Checking a Large Routine. And what he said was, we're trying to address this. How can one check that a routine or a program in the sense of making sure that it's right? And he talked about proofs of correctness. He hinted at assertions and modular reasoning, and he introduced the use of ordinals for determination. But this paper is a sort of historical relic. It doesn't appear to have been cited and affected the course of future work. So what I work on is model checking. As mentioned, model checking was awarded the 2007 Turing Award. The recipients were Ed Clark, Joseph Sifakis, and myself. And the idea is to algorithmically verify correctness of a finite state system or a system that can be represented in a finite state way. And correctness of these systems is specified in some logic, frequently temporal logic, which is a formalism for reasoning about change over time. And there's a sense that we want to describe long or infinite behaviors. What's different is that there are no proofs, as one would find in Turing's and subsequent work on verification. Instead, one searches through the state space or state graph of the program for certain patterns associated with the temporal logic specifications. The issues that come up are expressiveness and efficiency. How do you know that your temporal logic can express the properties you need to capture for your applications? And over time, we've developed a variety of new logics that are expressive and facilitate efficient model checking. And efficiency in general is an issue because the state space or state graph can be immense. We have the so-called state explosion problem, where the number of states is or can be exponential or worse in the size of the program text. And another feature of model checking is that it addresses pretty much symmetrically correctness and possession of of an error. Okay, so there are lots of bugs there that the Ariane 5 rocket exploded due to an overflow, and it cost $500 million. The USS Yorktown was a Navy destroyer, and they were using some off-the-shelf software. A sailor entered a zero into the software, and that computer crashed, and the crash propagated and left the ship dead in the water. I mentioned the near-nuclear war. There's the famous or infamous Pentium floating point division error, which cost Intel nearly $500 million. The Denver airport had a bug in the baggage system that cost over $1 million a day for 9 months. The Therac 25 radiotherapy machine, which was to treat cancer patients, had some sort of race condition, and it caused multiple deaths. So that's it.
Thank you. You need the remote, the slides?
Yes, thank you. Good afternoon. I'm not going to talk about verification. I am an ex-formal Methodist who moved to another area. 15 years ago, I got interested in systems and the system design, and this afternoon I will try to share some thoughts with you about the importance of systems, especially of reactive systems. I've been working on this topic. And in this slide, I say that a reactive system is a system consisting of hardware and software that interacts with complex physical environments. And I hope you understand that the shift of focus in information technologies moves from transformational software to reactive systems. So there are very important differences between transformational software and reactive systems. I hope you understand. Transformational software is terminating, deterministic, has a behavior that is hopefully platform independent, and we have some theory for that. And for reactive systems, they are non-terminating, non-predictable. They exhibit platform-dependent behavior because what counts is the behavior, the interaction between the system and the external environment. And to summarize, I would like to say that reactive systems are, in my opinion, the hardest and the most important type of systems today. Now, what's the status in system design today? Today, we know how to design at high cost 2 different types of systems which are difficult to integrate. On the one side, critical systems of low complexity and best effort systems. So systems that are designed in a more or less ad hoc manner, incrementally, and here the focus is not so much, okay, you should have some minimal availability, but the focus is on resource optimization. For tomorrow, we would like to have affordable critical systems. There are many application areas where we need cheaper critical systems technologies. And the challenge, I believe, is successful integration of heterogeneous mixed criticality systems. And here there are many visions. One vision is what people call the Internet of Things, how to integrate by using Internet technologies, networking technologies, embedded systems, cyber physical systems, and the challenge and the stake is huge here. And I believe that today this vision is not attainable because we do not have internet infrastructure of guaranteed trustworthiness. I think that what I'm saying is is clearly understood by most people here. Now, system design, it's different from pure software design, pure hardware design. It involves two main steps. One is going from requirements to the application software, and the other is implementing an application software in a platform that may be a multiprocessor platform by taking into account the available resources. And of course, the important question is how to bridge these gaps and how to ensure correctness. Okay, so what I call a rigorous system design, I think that we should try to formalize system design as a process that leads from requirements to implementations. And here I'm giving some characteristics of what I call rigorous system design. We need a methodology that distinguishes steps in system design. I think also that system design should be a unified process. Today, system developers, there is one development flow and another flow on validation, and the two flows do not, I mean, are not coherent. System developers use a big variety of languages that are semantically unrelated. I think also that design flows should be accountable. We should understand at each design step which properties may hold and why. And I think that we should overcome limitations of a posteriori verification by applying techniques of correctness by construction, by using provably correct reference architectures. Now the question is whether this is achievable, is attainable. I think that we should get inspired from two successful rigorous design paradigms. One comes from VLSI design. VLSI design could cope with exponentially increasing complexity of circuits, and I think they've been very, very successful. And I mean, it's very interesting to understand why it still works. And I come from the area of safety critical systems, and I think that it's not by chance that aircraft fly, and we have many, many systems that are safety critical that are trustworthy. Of course, the reasons of success are obvious. Design flows are transparent, coherent, accountable, and engineers are using a lot correct by construction design. Of course, these paradigms are just examples from which we can get inspired, but of course, the world of systems is much, much richer. This is my last slide, conclude. I would like to say that system design raises very, very interesting problem, and design in general is a very, very interesting problem. Formalizing design is a very interesting problem. How to link the world of the ideas to the material world, okay? And this is a very, very challenging problem. This is a problem that is posed to any engineering discipline, but especially for computer science and systems, this is a very, very important problem. Now, I have to say that system design has attracted very little attention from research communities, and that's a pity. I think that this can be explained by the fact that researchers prefer to work with nice theory and because design is by its nature multidisciplinary, because you have to relate abstract models to properties of the physical world. And here I would like to say that all the basic models of computer science, Turing machines, automata, completely ignore physical resources, physical time. And this is a challenge, how to enrich computer science with paradigms that come from control theory, from electrical engineering, at least for me. So just to finish, I would like to say that system design is central to computer science, and I think that ACM should work towards raising awareness of people on the centrality of system design. This will reinvigorate computer science, and this also will allow matching the needs for increasing system integration and new applications. Thank you.
this was fascinating. I want to move to the part where we discuss research versus practice. I have tons of questions, and we invite questions from the audience. I'll start with my own, and then I'll go through some of your questions. I wanted to ask you to help us identify in your past, present, people around you, research that make it successful in practice. What ingredients make it practical? What makes it feasible to carry it into industrial influence and into real systems? What effort do you personally recommend and can draw experiences from the past to help see through such impact? I already gave a teaser at the beginning. Alan Turing's universal machine may have not been as impactful had it had an instruction set that couldn't fit in the memories of the early computing systems. You may agree or not. Could you identify ingredients of success? Anybody jumping into that? Yeah.
I think you have to be at the right place at the right time. And that's just luck. So I think a large, luck is a very large factor in success in computer research.
So I think a very famous golf player, world champion, when he was asked about hole-in-one, whether it was luck or training, he said it's luck, but you need to train a lot to get that kind of lucky break.
Yes.
Yes.
I think there's a lot of synergism in the system building business. I should have mentioned that one of the greatest results of Multic system, which is a very ambitious system, was Ken Thompson's creation of Unix, along with Dennis Ritchie. Because it was a distillation of the essence of the better ideas in Multics into a small system, a viable small system, which could then propagate onward and still lives today in most of our personal computers. So it was a tremendous transmission, and it was all due to this sort of fluke of Bell Labs joining a big project, Ken being part of that project, Ken coming to MIT, absorbing from the things he stumbled into there, including the language BCPL, which had been Martin, I've lost track of the name.
Richards.
Martin Richards in England had put it on CTSS. Ken became familiar with it, was inspired to create B, the language B, which later I think led into the language C, and that too lives on. So there's a lot of synergism for being able to build on the work with the tools of others and be influenced by what others are doing. And it represents a certain generosity of the sponsors in putting money into ventures where they don't have always the best defined goals, but they do back people who have good ideas.
Else jumping into that?
I've had a little trouble hearing you. Oh, you're asking how does one do work that bridges the gap between theory and practice?
Research and practice, yes.
Yeah, research and practice. For me, it's worked out that I have some hazy idea of the practice, and I also can do the mathematical work, and so when it finishes up, it's reasonably well formed and applicable. I mean, and at the other extreme, I see people who are mathematically very talented, but they don't have a good grasp of the applications, and so the output of their work is not very applicable.
Okay, I would like to say something about the interaction between research and practice. I think that in computer science we have what I call the nice theory syndrome. Okay, we would like to have nice theory, or researchers, okay, like very simple frameworks that, okay, allow publication or whatever, demonstrate their cleverness, but when you want to see them applied to systems, to real systems, they fail, okay, to be used, okay? And this is, I believe, a problem with a lot of research that we've been doing in computer science over the past decades. I think that we should make an effort to, okay, to motivate the interest of researchers in practical problems. And there are a lot of practical problems, okay? How, for instance, to program, have good system programming languages, okay? I can talk a lot about that, okay? Today, programming technology is not adequate for system programming. So this is one problem for systems, okay? Another is how to have theories that allow you to get implementations that are optimized with respect to resources that are provided by a platform. This is also a very hard problem because you have to relate properties of your application software, which is immaterial, with the material world. And this raises very, very deep problems. The interaction between hardware and software, I cannot say anything about that. We cannot even model so if you want to talk about system verification, you cannot model even a very simple system. For instance, a node of a wireless sensor network. It's very simple as a system, but you don't understand how the application software interacts with the hardware. So there are a lot of open problems, very, very challenging, but I fear that research communities, okay, are not so receptive, I mean, or even ignore them completely. So we have this dichotomy, on the one hand, practitioners, and on the other hand, theoreticians. And that's a bad thing for computer science, I believe.
So we have a related question to that from an esteemed member in the audience. Would Vint Cerf like to articulate his own question, perhaps?
A mic to Vint here. Stand up, sir.
So it's Vint again. I've watched people try to prove correctness of programs and theorems and things and break their picks on that. Is there really any hope that we can make proofs like this, or is there some way of getting the machine to be more like an assistant? In other words, can we make a proposition, have the machine help us figure out whether that's a correct statement or not? When you were talking, Mr. Sifakis, about design, for example, it would be nice to be able to make an assertion about a design and have the system help us figure out whether that assertion is verifiable or not. Are there any interactive tools that we can use that would make this easier to make safe software?
Okay, so this is a question to me. Okay, so in order to assert some property, to be able to assert some property, we should understand what the system does. And if we do not design systems properly, in some, okay, talked about accountability and transparency of system design. I come from the area of safety critical systems. My laboratory has developed the technology used by Airbus, okay, or most of the technology of critical systems is used by Airbus. So in an Airbus, any line of software that runs on a machine can be verified, and can be verified just because designers have applied design rules and taken restrictions to make systems verifiable. And this is not the case for most of the existing systems that have been developed incrementally, okay, in some ad hoc manner, okay? And all in these large systems, System developers care only about tuning some parameters to get the best possible performance. I wrote recently in a book, in a paper, somebody saying that web application developers do not anguish about design. All they care about is about controlled experiment. And the title of the article was Controlled Experiment, okay, if you know the article, okay? And this is a very bad message for researchers and the students, okay? Because if these engineers do not care about design and care only about tuning parameters, so tuning parameters is in fact very good for performance, but you cannot achieve trustworthiness by tuning parameters because trustworthiness is a qualitative property. Your system is trustworthy or not, okay? And this you cannot achieve by tuning.
Yeah, Mr. Emerson, would you like to react to that? Involving humans.
Let me clarify the question. Okay. Are you asking if semi-automatic verifiers can be helpful?
No.
No.
Wait, let me get your mic.
The automatic verifiers are the things that don't appear to have worked, although I'd be happy to be taught differently if you choose to do so. I had the impression that maybe we could get them to help us, but we're the ones who have to figure out what questions do we want the machine to help us validate. And I guess I'm asking whether there are any tools that are more interactive. Is there such a thing as an interactive proof or an interactive verification?
It's a semi-automatic.
I guess that's what it is. It's the thing that when you pull the trigger, no, that's something else.
At Texas, we do not only model checking or fully automatic verification, but semi-automatic. We have the ACL2, thorough improver of Boyer and Moore. It's not automated. A human has to supply input. And you need an expert operator. But I would say if you pick a specific problem and fix it, then, get Jay Moore to operate it, then you have an outstanding chance of doing the verification. And the thing is, you couldn't necessarily do it in a routine fashion, all right? That just apply it over and over and over, which is what model checking excels at, okay? That it's automated and we can just keep applying it. And that's why it has been adopted widely in industry. And I think that the semi-automated approaches mean that the companies need an army of mathematicians or people with PhDs in EE or CS or mathematics. But that's it's actually kind of an alternative paradigm for verification. I don't know, it's analogous to having medical doctors that are true experts, whereas model checking can be used by verification engineers who don't understand exactly how it works, but they understand the design.
So let's switch for a few minutes to the operating system, folks. We have a question, again from an esteemed member of the audience, Dave Patterson. Would you mind stepping to the microphone and asking your question?
Raise your hand.
There we go.
Hi, this is for Ken Thompson. You worked on Bell, the chess playing program. At least I was surprised when the computers beat humans, and I understand now computer chess, humans don't even put up a good fight against computers. So was that surprising to you when that happened, or did you fully expect it based on your Bell experience?
I completely expected it and predicted it a little late. There was all of the participants in about the 1980 computer chess championships were asked if and when computers would beat the world champion. and my prediction was 2011. Most of the predictions were like next year or 5 years, way optimistic. No, the answer is no. If you look at Moore's law on computers and you look at the increase in speed with strength with speed on brute force computer chess, never is just, you just can't predict never. It had to happen.
Do you think like Go then is in the targets of computers then?
No, I don't think Go is in. If I had to predict Go, I'd predict way out. And the reason is because it's a very different kind of game. It's theoretically the same game, but in practice, it's a very different game than chess. It's not as tactical.
So I think that's a great question to put to the audience. So Go. When does a computer crack Go? And I will start with 100 years and count down by 10-year intervals. So who thinks in 100 years a computer will crack Go? 90 years? Ooh, it's a little small. That'll take about 4% of the audience. Dahlia, you're in a better position. So stay at 90 years there. Give me a number. What is that? What percent?
Dwindling down. I don't know. Very few.
Oh, come on. Is a mathematician in the house? Someone can look. Alan, you're smart. Take a look around. Okay, so 90 years. Keep your hands up. 80 years. 70 years. 60 years. 50 years. I got the instruction. Okay, so 40 years.
It's going back up now.
It's going back up. So we have a kind of a 30 years. 20 years. Ooh, optimists. 10 years. So who thinks less than 10 years? Well, don't be shy. Keep your hands up. May I take a mic to that gentleman and ask him? I assume you have a Go startup. So tell us who you are and why.
My name is Alan Sima. I just believe it'll be solved. Put together the things that we're seeing in terms of analysis of facial expressions and all of those things. So it's not purely the logical problem, but it's also a human and logical problem. I think it'll be solved in less than 10 years.
Spoken like a true poker player. Okay.
So my follow-up question to that would be, will it be a Unix-based or a Multics-based operating system that will do that? And actually, this is a very serious question. There's a follow-up question from the audience from Ken Poo. Do you foresee simple operating systems, such as Unix and its offspring, such as Linux, having a longer lifetime than other operating systems? I would like to add a quotation from Dennis Ritchie, the late Dennis Ritchie. A few years after reflecting after the Turing Award, he said, "In most ways, Unix is a very conservative system. Only a handful of its ideas are genuinely new. In fact, a good case can be made that it is, in essence, a modern implementation of MIT's CTSS system. This claim is intended as a complement to both Unix and CTSS. Today, more than 15 years back then, after CTSS was born, few of the interactive systems we know of are superior to it in ease of use. Many are inferior in basic design." And so I guess the overall question is, are we seeing fundamentally new challenges? Is the cloud fundamentally different from a multitasking operating system, or are we still recycling these old ideas of Multics? What is there to invent? What are the new challenges? And what will be the next long-lasting operating system?
Wow. I firmly believe that the when I was giving my list of things that I complaining about in my first speech, my 3-minute speech, I left 4 things out.
Only 4.
And one of them was operating systems and growth of complexity. That Unix had 20 system calls at the very first, and today Linux, which is a direct descendant, has over 1,000. So, but it has those initial 20. So I just worry about the complexity and the size and things that are grow. They never get smaller. They just get bigger and bigger. Your question. I don't know. I don't see much hope. I'm sorry.
Could I ask you, is Android Unix, is Ubuntu Unix, is Chrome OS Unix, is Windows, I'm sorry, is iPhone iOS Unix?
Well, I think operating systems in general are going to disappear because the home maintenance of the operating system is terrible. That Turing trying to get his computer up would I've seen my wife struggle. It's just terrible to see people spend their time doing system administration on one computer in a hallway. I think that the so-called evolution is that an operating system is going to be nothing but a screen that's shipped over a wire to the cloud, and I think that's the evolution, and that's definitely going to be what happened. And I hope that companies don't try to monopolize the cloud. Where you check in and you don't check out. You know what I mean? I'd like to see where from a user's point of view, you can't tell whether you're running on Amazon or Google or somebody else's piece of the cloud. That I really wish they would get together. Now, I have no hope for that. Absolutely no hope. I've seen companies hijack standards to such an extent for, I guess, competitive advantage, short-term competitive advantage, that I just don't see how a universal cloud computer will ever come to be with existing company dynamics, the way companies work.
Yes, Mr. Corbato.
That stimulates a lot of comments. I think one of the problems is that these computer companies accumulate some very good creative programmers who each feel they have to somehow surpass their predecessors. And they keep adding things to their systems because you can't easily take them out. And pretty soon the systems begin to resemble gigantic tar pits, to use Fred Brooks's term. I think even Apple, which started out with a relatively modest, simple system with the Macintosh, is, in the eyes of many, beginning to gum it up. It's getting increasingly difficult to explain to a newcomer what the computer is or what the operating system is, and trying to rationalize all the different twists and turns and trying to explain the nuances of what's going wrong when something goes wrong is getting to be more and more difficult. I share with Ken the experience of trying to help my wife to use her own computer without turning her into a system programmer, which she's not. And it's becoming more and more difficult to not only unravel it sometimes, but to explain it in a way which will persist. Let me go on to make another comment about the cloud. To those of us who were doing early time sharing, one of the key things we had to worry about was here were people putting their lifeblood, their programs they worked hard on, online and not keeping any copies for themselves. So we worked really hard to make the computer remember their information in spite of the fact that the hardware itself was flaky and often failing. So we had lots of backup and lots of... Furthermore, the people that were using our system knew who we were. And that is one of the things that worries me the most about the cloud. here I am working on a project which may be my life work. I'm putting it in the cloud, and suddenly the company decides to go belly up and it just says, sorry, we're out of business. Where is your information? God knows. That's unacceptable. And there will have to be some real disasters before people realize and wake up that they can't trust the cloud unless they know exactly who's behind it and what their liability is if things fail. Because sure enough, somebody's going to have a huge disaster with the cloud one of these days.
Okay, so we have 1 whole minute left.
Okay.
I thought I would give each one of you a really, really quick chance to say one wrap-up sentence. My teaser will be, but you don't have to address that. If you had to look under your noses, not 20 years from now, not 50 years from now, but really under our noses, where's the next breakthrough or really important thing to work on will be right now? Let's do this. Let's start with Mr. Sifakis at the end.
Okay, I talked about design. I think design is a key issue, key topic in computer science. If we are not successful in designing a trustworthy system, I think that we will hit some wall regarding the integration of systems. Okay, because currently the infrastructure is not trustworthy enough, and if we want to move to have increasing integration, this will not be achievable. And by the way, I had a question about having reliable infrastructure, operating systems, middleware, when this is going to happen, because this is a source of problems today. So for me, this is the challenge.
Okay, moving on, we have a tweet asking...
So actually, well, he just used up the panel's last minute. So could we just go across the panel here and get their quick answers?
Yeah, the tweet asks you to be optimistic.
I think in the future we may see program synthesis, algorithmic program synthesis for certain classes of programs be successfully pursued. It shares a lot of the same technical machinery as model checking, actually.
Oh, you cured me of predictions by showing those clips before the panel, especially when it's being recorded, so I'll pass.
It's okay. It's okay. The conference proceedings are going to be stored in the cloud, so there's no danger anybody's going to see it.
I have nothing profound to say beyond I put my faith in the bright young minds that are coming along.
Okay. Thank you very much.
Give the panel a hand. Thank you.